Good morning, everybody, and welcome to Astronomy 100. Today is October 11th. We are in week 9. Again, this is for Astronomy 100, and we have quite a few things this week that we really have to take care of. The two biggest things, or at least the thing that cannot be altered in one way or the other, is this Wednesday. We have to go out and in the evening at night and look at the moon. You really don't need any binoculars or any telescope or anything like that. This is with your own eyes based on observations. You're going to see where the moon is in the night sky. You're going to locate it basically. Is it toward the south? Is it toward the north? Is it toward the east? Is it toward the west? Or is it somewhere in between those directions? Is it right with the horizon, or is it above the horizon? Is it way above the horizon that it's really immediately above your where you're standing when you look up? That's your basically zenith, or is it somewhere in between? Okay, and how far basically? Again, I'm looking for approximate positions. I'm not looking for exact numbers. You're not going to give me the declination or the right ascension. Those numbers, probably if you open Stellarium, it's going to give you those information at that time, but we don't care for those. All we care for is actually an approximate position and the shape, how it looks like, okay? And you have to sketch that shape on a piece of paper. Down the road, you're going to transform it into the report and upload it. So this is for this Wednesday. It is critical that it has to be done this Wednesday. So again, as an item of discussion, do not forget to go out on Wednesday night, okay? I looked at the weather for the location of the campus and nearby. It doesn't look like there is any kind of disruption. It doesn't look like there is a, how should I say, any clouds or any kind of weather. So there is no problem. So Wednesday is the day. It's probably a good idea to go on Tuesday evening and at night and practice, not to report anything, but just to enjoy basically the night and see the different objects in the sky. Among other things is the moon. Okay. Of course, the data that needs to be done is on Wednesday night. Okay. So Wednesday the 13th is the day when you're going to have to go out. So as an item of discussion today, do not forget to do your observation. This is critical, okay? Because if you miss it, there is no way we're going to basically undo this and come back and fix it. You cannot, so it has to be done this Wednesday, okay? Now, that is one thing. The other thing that is also this week, and hopefully I will spend some time on it, is the homework. We have a homework from the previous week. So we have to go through those concepts and try to understand them and see what they are. And the homework requires some work, okay? Requires some honest, basically hard work. It is not due until October 30th. It doesn't mean that on October 30th in the morning, one decides to start working on it. You have to really start working on it as soon as possible. You're free to consult any kind of resource that you find useful, including actually and encouraged to do so to work with your classmates. So this is for the homework, okay? Other than that, in terms of content, we have the stuff that we've been used to. We have chapter 48 or unit 48, I don't call them chapters in this book. So basically so far, in terms of content, we explored several topics from the solar system because the course itself covers basically both the solar system, which is really a long topic by itself. Sometimes we teach it separately from the rest of the universe because of its length, the time we spend on it. It's a lot. So we're not going to cover the entire solar system in depth because we have other things to talk about too in this class, namely the stars, the universe as a whole, the galaxy, and other things that are of interest to astronomers too. So we need to explore those. So we're going to be talking today about ice words. What I mean by that is I'm not talking about the gas giants. I'm not talking about planets at all. We're talking about the smaller objects that fall in the category of one of two, either satellites like moons or dwarf planets, basically small objects that are mainly made out of ice, water ice, and other forms of ice too, frozen basically, other liquids. So that is basically the type of topic that we're going to be covering today. So let me share the screen and see exactly where we stand on things. Share. Okay. And let me just make sure. Oh, it's fine. I don't need that for it now. Okay, so this is the objectives for this week. So I'm going to open them. Of course, we have this week the project. Don't forget the other projects also, the retrograde motion of Mars. That is also an important project that we have to finish. Those are the emphasis at this point. The biggest really one is the lunar observation that has to be done, start this week, okay? So you cannot really delay that because it's really based on hard observations. It's not like on a guesswork or based on a Googling things or anything like that, or reading in a book or reading somewhere else. This is you yourself. You have to go into the field. You have to go outside and actually document your observations. So that is the purpose of the object, the project, and that's what you have to do. So this week on Wednesday, the 13th, you have to go outside and take care of this. Nobody else will do it for you. It has to be you, okay? Now, if there is compelling problems, I need to know about them as soon as possible. I really don't want to wait until when the report is due and then all of a sudden we have other emergencies that popped up on such and such date. And is there a way for me to recover from that? I would honestly urge you to really reach out as soon as possible. If something is really, you have something that might prevent you from doing what you're supposed to be doing. But the observation is tonight. You need to document the time, not tonight, I'm sorry, on Wednesday night. You need to document the time when you go out, the location, and so on and so forth, okay? So this is for the projects. There is another item in here I did not talk about that much in the objectives, but we're going, because it's still kind of due later, because I didn't want to really conflict too many things that are due at the same time. So I'm giving a little bit of room for it, okay? Actually, the homework, that's what I'm alluding at, is normally it's due the 23rd, but because I know the project, the second project, the retrograde motion is due on that day, I want to make sure to put some priority to this projects, okay? So the homework is given a little bit of room later on for it when it's due. So this is how the layout is. Again, the topic in terms of content for this week is the icy objects. And in here, you can see their sizes in comparison to Earth, okay? And also to our moon. And you can clearly from glancing at this, that the moon is of comparable size, actually slightly smaller than Io. Io is a moon of Jupiter. It's the closest moon of Jupiter to Jupiter, okay? Europa is slightly less. That's the next moon in terms of proximity from Jupiter to Jupiter. And then you have Ganymede. Ganymede is by far the biggest moon in the solar system. Actually, it's bigger than a planet, bigger than Mercury, okay? Callisto is of a big size too. And it's the third moon in the solar system. The Earth is moon and Io of comparable size, but Io is still bigger, okay? So, and then you have Titan. Titan is the moon of Saturn, and it's just second to Ganymede in terms of size, okay? So we have Ganymede, Titan, then Callisto, then Io, then the Earth's moon, which is a big moon, okay, when it comes to sizes. Obviously, those are not the only moons in the solar system. There are far more moons in the solar system. Jupiter by itself presents some 70-something moons. Saturn also comparable number to it. So the number of moons is large if you start counting them. As a matter of fact, these are not the only moons listed in here. You have Triton and you have Charon. Those are also moons too. Charon, there is kind of, or Charon, some other people they call it, is sometimes is not classified as a moon, but rather as a dwarf planet on its own right, because of the fact that it's big, relatively speaking, to Pluto, and Pluto is actually a dwarf planet. It was believed at some point that it was a planet, but we know it's not. At least according to the new definition of planet, and if it's allowed to be a planet, then it's not only it. Eris need to be also considered a planet. As a matter of fact, all of the other objects, Orcus, Haumea, Quaoar, Makemake, and Sedna, also in addition to Eris, has to be considered also as planets because they orbit the sun too in the same fashion as Pluto does. Okay. In terms of mass, as a matter of fact, Eris is bigger than Pluto. Okay. So that's why the definition came about, to reclassify what a planet means and what a dwarf planet is. So that's really what the need for it. Okay. So again, Charon is sometimes not classified as a planet, but rather as a dwarf planet. It and Pluto, as because they orbit one another, so, and they don't orbit on. I mean, let's say, for example, you take the case of the moon. You have the moon and the Earth, our moon, I mean, the Earth's moon, and the Earth. The moon clearly orbits the Earth. Well, not only that, of course, because it's a binary system, the Earth also must orbit, because as the moon is on this side, the center of rotation is not exactly the center of the Earth, but slightly shifted. So when the moon is in the other side, the Earth also has to move. That is because of the conservation of momentum, okay, angular momentum, that is. So they orbit a certain point where the Earth also is orbiting, but the center of rotation between the Earth and the moon, because of the huge size of the Earth, is very close from that of the center of the Earth. So for all practical purposes, the moon, Earth's moon, orbits the Earth, okay? But Charon is too big for that. As a matter of fact, it's 12% the size of Pluto, to a point where the center of rotation is not exactly inside Pluto. It's slightly off of Pluto, so that they both orbit that point. So it looks like it's a binary dwarf system. That's how it's classified at some, by some astronomers. So both of them are dwarf planets, and they orbit a common center of rotation. They orbit a common point, like any other two systems, by the way. And that common center of rotation is clearly off of both of them. It's not the side inside in either, especially Pluto, because Pluto is the bigger of the two. So it's believed to be a common point. Now, this is not the entire picture, though. Okay, for the Plutonian system, there is actually 4 more moons for Pluto. So it's really a big system by itself, albeit it's tiny in terms of mass. Okay, and then not only this dwarf planet has moons, all of the other dwarf planets also, for the most part, have satellites. Not for all of them, but some of them do have satellites, moons, if you like to call them that way. Okay, so this is basically the system that we're talking about in here in terms of icy worlds. Of course, the Earth's moon is not icy world. The Earth's moon is made of silicate, and it has a density of approximately 3.3 kilograms per cubic meter, or 3.3 grams per cubic centimeter, indicating that it's really made of rock and minerals for the most part. Okay, doesn't have any icy structure. But the others, for some reason, for most of the time, they are icy objects, with the exception of Io. Okay, Io, in terms of structure, it looks like it has lost for the most part its ice. It must have been no different than probably Ganymede in terms of size and in terms of also structure, okay? And in terms of ice, basically the crust, surface crust. But because of its proximity from Jupiter, it must have undergone a lot of tidal heating. And so today we already have had one item that I mentioned. There is another item that I want you guys to experience, and that is the tidal forces. Okay, trying to see if I have a paperclip in here somewhere. I want you to really report on this. Okay. The paper clips, you usually have a bunch of them laying around in here. I thought I had them, that's why I did not go outside and look. Okay. I really need paper clips, so I'm going to pause for a second in here to demonstrate the point in here with tidal friction. I have so many things in this. You probably have experienced this one, so it may not be that hard to do. Okay. Paperclip would work a lot better with anything than anything else, but I'm sure that you have experienced it yourselves. It's basically friction produces tidal forces, and those forces, you can see them by the energy transferred in the form of heat. So let me grab paperclip and I'll be back. Okay, 1 second. Where is the camera here? Here's the bag of goodies. Normally, it's usually near me. For some reason, it's not. Grab a bigger one. Right, so this is what we got to do, okay? The smaller one. Okay, this is what we have to do today, okay? In addition to a report on that, okay? So I'm gonna grab a paper clip like this one, the one I have before me. So what I'm going to do in here is I'm going to basically play with it a little bit back and forth, twist it, just like what's happening to this planet, okay? And if I do it fast enough, okay, hopefully just before the breaking point, like it happened right now, you feel the heat inside your finger. So this is what we're going to do. Of course, this is an energy that caused this paper clip to break in here. So you're going to grab a paper clip and you're going to play with it a little, and then you're going to do it fast enough to report the heat. And then at some point it's going to break, indicating that an energy was required to cause that. So here is what's going on with Io, so that we have an understanding of what's going on with it. On one side, it's being pulled by Jupiter as it goes around Jupiter, okay? And it wants to go in a circular path, close from a circular path, at least in its elliptical path. So it wants to be on its orbit. That's basically the point in here. So you have, let's say, for example, this is Jupiter. On one side is Jupiter, and the other side is Io. But in addition to that, you have Europa, which is not too far from both of them. And there is a synchronicity in here. There is a resonance, it's called, between the motion of Europa and the motion of Io. Io goes twice around Jupiter, whereas Europa goes only once in the ratio of 2:1. Meaning, let's say, for example, both of them are on one side right now. So here is a problem. On one side, Jupiter is pulling a lot on Io. On the other side, Europa is pulling, but not by much because it's smaller size, but it's pulling nonetheless. So there is this pull in here. On the other side, when this one moves, the other one is still on the other side. And in this case, both of them are pulling on the other side. So now the force changes. So it's the same thing as I was doing earlier with the paperclip. So there is this pull that is at sometimes bigger than the other side, and this will shift its motion. When both of them are pulling on one side, they bring it closer. When Europa pulls on the other side, it pulls it further away from Jupiter. So its path is not really circular, and it cannot be. It's kind of highly eccentric to some extent, which is one reason why its shape is actually changing. It's basically reworked all the time. And this, of course, causes heating, exactly like I was demoing with a paperclip. Okay, those internal heating will cause all kinds of problems. That's probably what happened to the crust that was made out of ice in the past. It must have melted because of this energy, and it was lost. Okay, as a matter of fact, if we look at the next picture, this eruption, which is the volcanic eruptions in here, since basically the eruption is several hundred kilometers from the moon, to the point that they're actually going into Jupiter itself, being attracted to Jupiter, okay? And those fast-moving particles will cause all kinds of auroras when they arrive to the atmosphere in there. So, and especially because they are driven by the magnetic field of Jupiter. So this really is part of the problem what happened to it too, okay? Now, it left it poor in water in terms of ice form. And the main component is actually the sulfur. The sulfur is what gives it it's this kind of a yellowish color, okay? So these eruptions are very, very concentrated. As a matter of fact, there's a picture in here, in graph B, shows more or less the activity. As a matter of fact, there is a volcanic activity in here which still glows in the form of a lava flow on the surface. In terms of volcanic activity, this is the most active body in the solar system. So Io being so, okay? Io, Europa, Ganymede, and Callisto. As a matter of fact, the first three were discovered one night. The next night, Io was discovered going around Jupiter by Galileo in the year 1610. Okay, that's why they're called the Galilean system. The closest one to Jupiter in terms of proximity is this one. So the reason why we classify it as an ice world also is because of the fact that it must have had ice also forming in the same plane, because they are all orbiting the same plane of Jupiter, indicating that they must have formed basically with Jupiter. These are not captured moons or anything like that. So these are the four moons called Galilean system. Okay. So this is basically part of the structure in here for this. Now, in terms of internal structure, like I said, there is the crust in here. There is no ice in here because of this activity. So the density, the way that we were able to basically measure its eruptions, the way that we basically, in terms of lack of water and all of that. So this is how we speculate its structure is, because it still has a high density. As a matter of fact, its density. So there is a rock and mineral structure for it right now, but in the past it must have formed in the same way that the other three moons of Jupiter did. Okay, so this is the closest moon. Now, in terms of the next moon, in terms of proximity, is Europa. Europa is shown to have a, of course, in terms of the outer layer, it looks like it's, first of all, when you look outside, when you look at the surface of Europa, you see it's marked by these lines in here, okay? First of all, the bright regions of it, the white regions of it, those, they must be ice, mainly in terms of icy structure. So what are these lines? They're mainly water, basically cracks inside the surface of Europa. So whatever caused the volcanic activity on Io is similar, because also Europa in actually also not only in being pulled by Jupiter and Io on one side, but it's pulled by Ganymede on the other side, and Ganymede is a big moon. Okay, and it's also in resonance with Ganymede too. So the forces that causes the similar tidal forces in here on Io exist on Europa, which causes cracks in the crust, which is mainly ice, and those cracks, they have eruptions of mineral-rich water. This is basically what you're looking at in here. Okay, So those are the crashes where the plates of the ice starts to rub against one another, and this leads to basically a flow of liquid from inside. Now, not only that, but you have this dots in here, freckles. They appear to be in a similar formation, except that from some sort of volcanic activity. So if you look at the surface in here, when you compare it to this surface, this is less cratered in terms of Io versus that of Europa, which has a little bit of craters, and that indicates somehow that this surface, although it is geologically active, it's a little bit less in terms of this activity compared to, relatively speaking. In terms of the structure, because of the magnetic field that this moon has, and because of also these eruptions, we think that there is an ocean that is very deep, and the estimates put the ocean there, the water there, as more than the water that all of the Earth has. So this is under the crust, there is liquid water, and this liquid water must be salty because of the presence of the magnetic field. So salt in this case will give it the conductivity necessary for it to have the currents when it spins, creates a magnetic field. So again, this is the model that we have for it. Because of the high activity, because of the heating, it must have been differentiated where the heavy minerals, in this case, iron and nickel, must have settled into a core of some sort. And then you have a mantle in here, which is a rocky structure. Again, the density, based on the magnetic field, this is how we think in terms of the internal structure for Europa is. So it has a lot of water in here, to the point that astronomers think that, at least scientists think that it could harbor life as we know it, meaning carbon-based life in the oceans in here that are rich from in terms of minerals. Not only that, it must be because of the tidal heating. Again, you have at some point in the life of Europa, it's being pulled by both in the same time, Jupiter, and to some extent, even because it's close by it, Io. On the other hand, you have Callisto, which is pulling it on one side. So it's being pulled one side by Callisto and the other two on the other side. When it moves around, because of, again, the resonance, all of the other three moves, because the numbers are in proportions, okay? So at some point, you will have Jupiter, which is always there, and you will have Io, and you will have Ganymede pulling it on one side, pulling the entire one. So they bring it closer to them, and then on the other side, at some point, Callisto will help it away. So again, because of the same idea as what's going on, it has this high activity in there. So that what melts, because of the heat that is generated by these tidal forces, that what melts the ice under this protective shield of ice in here. So that is basically why we have these oceans in there. So there is all kinds of interest for this one, to the point that there are some missions that are planned to go and see if we can dig through this is several miles away. I mean, the ice structure itself. This requires some heavy technology to be able to penetrate it and see what's inside. Obviously, the easiest point is through the cracks themselves, okay? They must be easier probably to access the surface water, I mean, to the water underneath the surface. But that's some of the things that we're thinking about this moon. So in terms of size, as I was saying, Europa is not big. As a matter of fact, smaller than our own moon. But in terms of interest for scientists, it's really a very, very important object. Now, if you look at the surfaces outright, you will see that Ganymede and Callisto, both of them are heavily cratered, indicating that because they are further away from their planet, host planet, namely Jupiter, they are not seeing as much, basically, tidal forces. They are not seeing as much as geological activity because of the heavy craters that they have experienced. But their outer structure is no different in terms of being an icy structure. Suggestions that maybe they have also similar structures underneath where there is actually probably a liquid surface in there. Again, the densities will help a lot in terms of understanding them. So this is some of the objects in here in the solar system. I know for those who came in late, we have had already a couple of points that we mentioned, and it's no problem reminding you again about them. The first one is, the first point of discussion is to go outside and do the observation on the 30th, this Wednesday. So this is very important. So this is a reminder in the discussion to put it in there that this week we should go outside and do our observations. We cannot skip this one on Wednesday. The second point that we did in here is I did a demo that I want you guys to do also with a paperclip. With a paperclip, basically, before I broke it into two pieces, okay? Where I started basically working on it, simulating the tidal forces, because that's exactly what the tidal forces do. They take a moon, like for example, Io, and they start to pull it one way and the other to the point that heat is generated. So we're trying to replicate that effect. And then at some point, actually, if you continue with this one, this is exactly what happened to it. It breaks into two, okay? So these forces can be dramatic, and that's exactly what's going on with this one, to the point that Io lost its ice. And it's still an ongoing process, still releasing a lot of energy because of this effect, because of the tidal forces. Okay, so the tidal forces in this case are the effects of both, for the case of Io, the effects of both Europa on one side and Jupiter on the other. For the case of Europa, it's actually the effects of Ganymede from one side and both Io and Jupiter on the other. As a matter of fact, the situation is a little bit more complicated for Europa if you think about it. Because resonance is resonance, meaning the ratios are constant all the time. So for Europa, on one side you have Ganymede, on the other you have both Ganymede and Io. But Io and Ganymede, they are not in the same side on both of them all the time. So actually you have both of them on the same time, and sometimes they are twisted, they are backward, okay? So in this case, the effect is slightly less because it's going to be mainly Jupiter in that case, because Io will be way on the other side and far away, so its gravitational pull will be less. So in this situation, and if you take also, let me try to draw this one to see, to understand that the problem is a little bit more complicated for the case of, let me stop sharing, and let me share the notes in here. And let me create a new page in here, call it week 9. So let me try to draw and see the different situations, because the ratios are, again, I'm going to draw, here is Jupiter, here is Io, here is Europa, and here is your Ganymede. Okay, they are not drawn to proportions, either whether distance or size. Okay, this one goes twice when 2 times before this one goes once. This one goes 2 times before this one goes once. So around Jupiter, of course, they're too small to shift the center of rotation away from Jupiter. Jupiter is supermassive planet. It's the biggest planet in the solar system. So here is the situation. At some point, we have this configuration exactly. So we have Jupiter, Io, Europa, and Ganymede, okay? So you have the effect of Jupiter, which is big, the effect of Io, which is small, and the effect of Ganymede, which is okay, if you wish, okay? So this is the configuration. So the planet is shifted one way. At some other planet, some other time, you have Jupiter, you have Io, you have Europa, and you have Ganymede. So in this case, Jupiter is pulling still with the same effect. Now, Io is still pulling with the same effect. And also Ganymede is pulling, but a lot less effect because of the fact that it's further away. Remember, the force of gravity is inversely proportional to the square of the distance. Okay, this distance is obviously smaller than this distance. So in this case, the effect is less. This force will be less. But it's nonetheless, all the forces are pulling it toward one point in sky. So that is one configuration. Again, Jupiter, we're not going to move Jupiter at all from this picture. At some other point, you have Io in here, and you have Ganymede in here still, and you have Europa by itself on this side. So Jupiter is pulling on it. First of all, Ganymede is pulling with the same effect, but now Io is a lot less. So this effect is less. Okay. And what other situation? Oh, yeah, we still have another situation where we have Jupiter still, we have Io, and we have Europa, and we have Ganymede. So in this case, this is the effect of Jupiter is always there. The effect of Io is still similar to this effect, and now the effect of Ganymede is similar to the first situation. So you have, the problem is complicated. So for Europa, its path is complicated because of this fact that you have the forces that needs to be each person, I mean, each one of the three members, they're pulling on it because of this simple ratios of 2-to-1 and 2-to-1, okay? So this is basically, and even if the case of Io, I have simplified it because I took only Europa, but Ganymede can have an effect, but Ganymede is far away. Now, you throw in the mixed Callisto, and now you have the system is very complicated, okay? The system is very complicated. And this is because they are big moons, okay? This is really although Callisto is far away from the others and it's smaller than Ganymede, so its effect is a lot less, I mean, negligible. That's why we never really discuss it when we're talking about the tidal effects in here. So the tidal forces are a very important component in this equation, and we really have to, and it's not an easy clear cut, especially for the case of Io. For the case of, I mean, for the case of Europa, for the case of Io, it's a little bit easier, okay? Because you're going to ignore Ganymede just as much as we're ignoring Callisto right now. You're going to focus only on the these three objects in here. Would you always put Jupiter in the same point? Jupiter is not going to move that much. It's not going to move at all, practically zero, okay? Because of its sheer mass. So let me go back into the stop sharing and then continue the discussion. Share. So I think this is an extensive topic in here. The next object that I'm not mentioning in here, it's of extreme importance, is Titan also. Titan, the moon of Saturn, it's a big moon. It's actually the second moon in terms of size after Ganymede in the solar system, okay? And Titan, if you look at the outer surface, you don't look much. It just looks like Venus. Why? Because it has a super thick atmosphere. As a matter of fact, its atmosphere is slightly more heavier than that of the Earth. The pressure there is slightly more than the pressure on the Earth. I mean, if you were to stand on the surface, you wouldn't feel much difference in terms of pressure. You wouldn't feel like you have to wear a pressure suit, for example. For the case of Mars, you have to really have a pressurized suit. Otherwise, you're going to explode. Basically, your insides will come out. And in the case of Venus, you have to wear a pressure suit in this case to lower the pressure in there, because the pressure outside is too much. Because if you don't wear it, you're going to be crushed. Okay. So really, this is the situation here. For Titan, you wouldn't need that. However, the temperature is extremely low. So low that the surface, the atmosphere is mainly made out of nitrogen, like the nitrogen we know in here, but to extreme temperatures in this case, that the methane, which has a chemical composition of carbon CH4 basically, or ethane, which is C2H6, that both of them are actually, they exist like water exists on here on Earth. They go through precipitation, they go through liquid form, and the evaporation. So there is a cycle in there, similar to the water cycle on Earth, but that of ethane and methane on the surface in there. On the surface itself, from outside, it looks like there is oceans in there, or at least lakes in there, okay, on the surface of Titan. But those lakes are not of water. As a matter of fact, there are rocks in there there is a rocky structure from outside. You look at it, but that's actually frozen solid water, ice, basically. And the water there plays an importance in terms of volcanic activity too. But instead of volcanoes erupting in terms of rock, molten rock on Earth, it's actually the molten ice in there. So that's really the cycle on Titan itself is a very interesting process, and it looks similar of what's going on Earth. Okay, with the exception that the liquid there is not water. The liquid there is that of methane and ethane. And then, so there is speculation that maybe a life form that does not, this is not carbon-based life form, that requires a different kind of energies that might exist in there. Of course, methane and ethane are highly combustible materials. The reason why it does not erupt in fire is because there is no oxygen in there. Okay, so that's basically as simple as that. And the oxygen that exists is combined already with the hydrogen to form the ice water in there. So otherwise the chemistry in there, and then you need to have high enough temperatures for the chemical reaction to happen, and the whole moon is a frozen solid. The reason why we call them ice words actually, and I forgot to mention that, is because they exist, they must have formed beyond the frost line, basically. So Triton, which is an interesting moon of Neptune. Triton is an interesting object in itself, okay, which is another moon. It does not orbit in the same direction where Neptune spins, okay? Neptune rotates in one direction. Most of its moons rotate in one direction. Triton now is in opposite direction. It is believed to be a captured dwarf planet when Neptune was formed and was interacting basically with especially Saturn and Jupiter, and they kicked it out. It has migrated. In doing so, it has captured some of the objects. Among them is Triton. Okay, and that's what explains basically its odd behavior. Okay, to the point that maybe it lost some of its moons too in the process when it captured some of this object during that interaction. Now it's settled in a position just outside of Uranus, and that's where the path of Neptune is. So those are some of the moons. Again, I talked already about Pluto and Charon, both of them, and there is a story behind them. When of course Neptune was discovered, and it was discovered based on calculations after Uranus was discovered by basically Herschel and some other astronomers later on, confirming its existence and so on and so forth. The point being in here is that you have Neptune that was captured, but its path exhibited kind of, at least according to the calculations, that there is suggestion that there is another planet past them. And there was a hunt for it, for that planet. It was called Planet X, and people started looking for it, trying to find it. Usually when there is a planet that is suggested, like right now we call Planet 9, which is where they're looking for it. And Planet 9 is part of this chapter, actually. This is the hypothetical Planet 9 that we're looking for it. Usually you look for it in the ecliptic, in the plane where all of the planets exist. So that's exactly what happened with Pluto too. That's what we were looking for. They were looking for it there until in the 1930s it was discovered. Obviously, the mass was estimated to be several times that of the Earth, or slightly more than that of the Earth, about 5 times that of the Earth initially. But there was no way for us to know its mass accurately or to be able to find its mass. The reason why you estimated this mass is because of actually there was an error in the calculations based on the odd path of both Neptune and Uranus, especially Neptune. So that's why we thought that its mass was about 5 times that of the Earth. But then when Charon was discovered, the moon next to it, then we were able to find its mass, and it's very, very small. It's 2,000ths that of the Earth, very small, okay? So it's not really a planet in that sense, in terms of mass, But that did not really, because later on we discovered that it has actually 4 more moons. And they are in this picture in here. And as I was saying in here, this is a system that is complicated enough. Later on, when the other dwarf planets started to pop up every which way, then a definition needed to come about to define what a planet means. I mean, and what a dwarf planet means. Not all dwarf planets, as we discovered from previous units, exist in the past Neptune, but some of them exist actually within Neptune, like the series, which is part of a project that I discussed in the beginning. Okay. In terms of shape, there is this odd shape of Haumea, suggesting that it's spinning extremely fast around its axis to the point that its shape is not circular anymore, or spherical anymore, I should say. So it has this odd shape. Of course, you have Quasar, you have Makemake, and you have other objects. If you look at them from this perspective, of course, Sedna, it was part of an assignment that we had a few weeks back from a homework assignment. Sedna has this very high eccentric orbit. At some points, it's very close from everybody, but at some, this is Neptune, by the way. And these are called the TNOs, trans-Neptunian objects. Anything away from Neptune. So think about where Neptune is. Neptune is very, very far from the solar system. So this is from the sun. This is where the sun is. So very close from it, you have Mercury, you have Venus, you have Earth, you have Mars, you have Jupiter, you have Saturn, you have Uranus. And they are not very close, they're very far. So that's, you know. And now we have Neptune. So anything outside of Neptune is a TNO, trans-Neptunian object, okay? And you have all of these dwarf planets, okay? For one thing in here, they're not all on the same ecliptic. And you have, of course, Eris, which is a very highly eccentric, Pluto, which is very, very far, and its study was very difficult until a flyby when we had this nice pictures of it, okay? We really don't know much about them in terms of structures as much. We have a lot of comparisons to how Pluto is. And then we have them, and we have Eris in here, which is way outside of the ecliptic plane. And it's big object, so it's in terms of mass is bigger than Pluto. And you have Sedna, which is a highly eccentric. Right now we're seeing it. A few thousand years from now, it's going to be on the other side of the solar system, where it's not going to be seen, even at least with modern technology that we're using. So that's really the problem for it too. So this is the solar system in a nutshell. Now, if you look at this path, there is a problem with them. With all of these TNOs, they seem to be affected by a central object. And that central object is a hypothetical planet 9. Okay, see Sedna, the orbit of Sedna, these are very, very highly eccentric objects. I mean, the blue one is where Neptune is, and it's a very far away object. You couldn't even see it with the powerful telescopes at that time. We really also had to use technology at that time, math, to predict its position. Sure enough, when we looked at it, it's moving there. It's moving extremely slow, of course, because of the fact that it's very far away from the sun. Now compare that to hypothetical planet 9 that is affecting these orbits. And that's why this orbit seems to have this common points in them. So right now, its position is probably somewhere in this region. And this planet 9 must be super massive planet, big planet compared to the Earth, of course, not as big as Jupiter is or any of the other planets, but it must be big planet. Even in its closest approach, remember Sedna right now is very far away. Even right now, it's in this position, somewhere in here. It's relatively speaking close. This is not going to even get near that point. That's what the hunt for it is extremely difficult. This region of the night, even though you're looking somewhere in the ecliptic on the same plane, is a very large region looking for a very light, dim object that does not emit any light whatsoever. It's reflecting the light from a sun that is extremely far away from it. So it's extremely dark, and you're trying to trace it, trying to find its position. Once you find it, you really have to find an object near it, like a moon or something that orbits, to find really a good estimate for its mass using the inverted version of Newton's, of Kepler's law due to Mr. Newton, the third law of Kepler due to Mr. Newton to find the mass of the object. That's how we found the mass of Pluto when we discovered its moon. That's how we usually do masses nowadays. Okay. So this is basically the entire stuff that we have for this chapter. Again, you're supposed to read the chapter and go through it and understand what's going on in it. Let me go back to discuss an important point because we still have the time for it and we have to, and that is the homework from this week. Of course, the unit is unit 48. I just basically gave you a summary of it. Hopefully you guys will go and read for more information on it. So again, all of these problems, they are from problems from page 319, okay? Let me make sure it wasn't broken here. The 319, I reported it but it doesn't matter, you have the numbers in here, you have the problems in here. This is from actually unit from the 6th edition. Correction. It's page 317 on the 5th edition, not the 6th edition is 319. So the information is correct. Okay, with the exception that it says either edition, this is not correct. Okay, it should really be on the 6th edition. But it doesn't matter because you have the problems in here. Okay, so you have them in here. You have the problems in there. And they're the exact same problems on either edition. So the problems you have 11, 12, 13, 14, and 15. And the first one, it says your Venus's atmosphere contains about 4.6. Okay. Let me try to probably do open my notes and see how we're going to have this answered, okay? So let me stop sharing the screen and go back to my notes from week 9. Hopefully you guys have the same problems now open before you. So let me share the notes now. Okay, what did I put the pen? Here it is. Okay, so what do we have in here? So problem 11, question 11. Okay. So right now it's the 8:55, so it's probably around 55th minute of the recording. So Venus's atmosphere contains 4.6. So the Venus atmosphere, they say contain 4.6 times 10 to the power 20 kilogram of carbon dioxide, CO2, okay? If all of the oxygen in the atom CO2 were combined with hydrogen to make H2O. So basically take CO2 and break it into O, the oxygen and carbon. Of course, you have 2 O's in here and you have carbon in there, okay? Take this O and combine it to produce water. Obviously, you're not going to need, you have to bring enough hydrogen for this to work. For that, you're going to make 2 of this and you have to have 4 of this, okay? I mean, you have to have, oh, no, just 2 of this plus 4 hydrogens, okay, to make it work. In some sort of a process, we're not detailing the process in here. So somehow, all of this oxygen is converted into water. We're trying to terraform this planet, make it into a habitable planet, okay? Instead of carbon dioxide, what would the total mass of the water be? So we want to know how much mass there is right now of this water. Okay, here is how we're going to rationalize this. In the CO2, and they give you some numbers on there, okay, note, Hydrogen has a mass, an atomic mass of 1. So hydrogen is 1 atomic mass, AM, okay? Carbon is 12 atomic masses, and oxygen is 16 atomic masses, okay? So we want to know, if we know right now, this is how much carbon dioxide, how much water we're going to get. So here is the rationale behind it, okay? What makes up this molecule? It's carbon and oxygen, 2 oxygens. So for CO2, the molecule itself is made up of 1 carbon, which is 12, plus 2 times 16. So it has a 44 atomic masses. Okay. Out of the 44 atomic masses, 32 are oxygen and 12 is carbon. So oxygen represents a ratio of 32 over 44 in the air, in the mass of the air, of the atmosphere. That's the ratio, because you have 32 out of the 44 is oxygen. The 12 is the carbon. Okay. But we know what the mass is. We know the mass is 4.6 times 10 to the power 20 kilogram. They gave us this. That's how much air we have right now. So 32 divided by 44 times this number gives me the mass of the oxygen. Now I need to combine that to find water. And water, H2O, has an atomic mass of, you have 2 oxygens, 2 times 1, because each hydrogen is 1 atomic mass, plus 16 from carbon. You only have 1 carbon. From oxygen, you have only 1 oxygen, for a total atomic mass of 18. Out of that, 16 of which is from oxygen. So 16 out of 18 in water is oxygen. So basically we have the numbers now. What I'm going to do is take how much mass of oxygen and versus this one. So it's going to be, okay, and if you don't understand this, please let me know, okay? I'm going to expedite this one, times 4.6 times 10 to the power, what's the number? 10 to the power 20 kilograms. Now, if I do this, I found how much oxygen I have. But I need to add to them, for each one of them, I need to add to them 2 atomic masses to form 18 atomic masses of oxygen. So how much I need to add to them altogether to produce 18 out of 16? If I do this math in here, quickly with a calculator, 32 over 44 times 4.6 times 10 to the power 20. By the way, I don't need to do the 10 to the power 20. I can leave that later on, okay? The reason why I'm saying that is once I found what everything is, so I could ignore this 10 to the power 20. I could do 32 divided by 44 times 4.6 times 18 divided by 16. Once I find that number, I multiply it by 10 to the power 20 so that I don't have to carry that 10 to the power 20 with me, okay? So when you're doing powers like this one, try to reduce all the powers together. Since in this case, I only have 1 of them, I just ignore that part for right now, do the other algebra. Once I'm done with it, then I append it at the end, and that's the end of it. But it could have an importance in terms of how am I going to represent it scientifically, and that's it. And that's no big deal. I should be able to do that. So times 18 over 16, over 16, not over 6. Okay. And the answer is 3.76 times, it's actually 3.77 because, no, 3.76, I'm sorry. I have to do the rounding in here, but you don't have to, again, times 10 to the power 20. Again, as you can clearly see in this situation, 10 to the power 20 did not budge. Stayed there. Kilogram. Okay, so this is the mass of the water that I can make. If I take all of the other oxygen and somehow find enough hydrogen, combine it from the carbon dioxide, combine it, this is how much water we're going to present. They tell you compared to this to the mass of the Earth, to that of the Earth. So if I do that of the Earth, how much time we have? We still have good time. Okay, so the Earth, so that's how much Venus would have water if we were able to terraform basically Venus and convert all of its water, all of its oxygen and the carbon dioxide into water. So this is how much water we're going to end up with. Earth has more water. Earth, according to the book, has 1.4 times 10 to the power 21 kilogram of water. So the Earth now, if I do the ratio, 1.4 that is, so how much Earth has more? It's 1.4 times 10 to the power 21 divided by, so Earth over Venus. So when they tell you to compare, always do a ratio like this one. So divided by 3.76 times 10 to the power 20. Again, I'm going to take what was 1.4 divided by 10 to the power 20 divided by 3.76 10 to the power 1.4 10 to the power 21 divided by 3.76 times to the 10 to the power 20. It's about almost 4 times, 3.7 times more. So Earth will still have more water in it, basically. Okay. So that's the moral of the story. There is more water on Earth, even if you were able, of course you should not, at least you should leave some in the atmosphere if you want to have greenhouse effect high enough to keep the temperature a little bit manageable in there. Otherwise the planet will freeze, even though it's closer to the sun, it will become too cold. You lose all of the atmosphere on it, okay? Case in point, look at Mercury on the cold side of it. It's really super cold. Okay. So this answer is 11. 12 now. From your answer to 11, how deep an ocean would this water produce if it were the same depth everywhere on the planet? Note that that 1,000 kilogram of water fills a cubic meter. Okay, we need to see the radius of the planet. Okay, radius of Venus. The reason why I'm saying that is, okay, here is the planet now. Okay, all of it is a sphere, of course, and the radius, the area of a sphere. And again, I will have some people who ask who did not watch the recording, and I'm going to refer them to the recording. So the area of the sphere, because it's not given in the problem. So you need to know this. The area of the sphere is 4 pi times the radius squared, and this is the radius of the planet. So we need the radius of Venus in order to solve this problem. Okay. So once we have that, we're in business. Okay. The radius of the Venus is slightly less than that of the Earth. And we can take it exactly 6,000, okay? So I'm going to open a new tab in here if you want to. Radius of Venus. Obviously, it's in the book in there. There's the radius of Venus, 3,760. I don't want them in miles. I want it in kilometers. Okay. Kilometers. I don't need to, or in meters, okay? Just giving the same information at this point, okay? Okay, here it is. In kilometers, 6,051 kilometers, 0.8. I'm not gonna use 60,051.8, I'm gonna use 6,050, okay? As I was saying, about 6,000. Oh, I'm sorry, I'm not sharing the screen, but you can find it from the book. It's about 6,000, okay? So the radius is about 6,000. 6,000 kilometers. You have to be careful in here. When you're doing this math, you have to convert it into meters. So 6,000 kilometers multiplied by 1,000, this is how many meters, this is how R is, okay? 6,050,000 meters. Now, this is the radius. I need to know the depth. So here is the story. I need to know the depth in here. Once I multiply by the depth, then I find the volume. So the volume is going to be the surface of the area, which is known, times the depth of the ocean. This is what I don't know. I know the mass, though. From the previous calculation, we were able to find the mass. So the mass of the water is 3.76 times 10 to the power 20 kilogram. And I know that 1,000 kilograms is a cubic meter. So I know the volume then of the water is equal to the mass divided by the density. And the mass, we found it to be 3.76 times 10 to the power 20 kilograms divided by the density, and the density is 1,000 kilograms per cubic meter. So 1,000 and 10 to the power 20 is 10 to the power 17. And so the volume should be 3.76 times 10 to the power 17 cubic meters. So all I have to do is equate these two volumes to one another. So I have to have 3.76 times 10 to the power 17 cubic meter must be the same as 4 pi r cubed, and r cubed is 6.050 point, not comma, point, this 00 squared. This is in meter squared times the depth. From here, I'm going to find the depth to be 3.7676 10 to the power 17 divided by 4 pi, and 4 pi is 3.14, okay, times 6.050000 squared. You do the math. You're going to find out how much it is in meters. It should be less than a kilometer. If you do the same math for Earth, it's going to be about 2 or 3 kilometers, okay, which is a proper magnitude for what the depth is. This is assuming that all of the water is spread uniformly and has the same thickness in here. In other words, the surface is smooth. Obviously, the surface is not smooth. So you'll have probably some oceans that are deeper, some points in the oceans that are deeper and more in depth than others, okay? But not that much compared to. That's why we think the layer that of water that existed for Venus in the past must be a thin layer, not as thick as the Earth. So whatever volcanic activity caused it to lose it quickly, okay? To lose it quickly. Otherwise, if it had probably the same amount of water as the Earth did, probably still have some water in its surface or maybe an atmosphere or something. So it lost it quickly. 13. We need to go faster now. 13. And again, if you have guys question, please let me know and be more than happy to discuss any of this problem. So Kepler's third law, which basically says that p squared is equal to a cubed. You guys remember from previous problems, describes planetary orbital sizes relative to Earth's orbit, which is assigned the size of 1 AU. One method for finding absolute orbital sizes is to use radar technology, radar ranging between planets. Use Venus's scaled orbit to be, so the orbit of Venus, A, is equal to 0.723 AU. So this is for Venus, okay? And they tell you on the observation that a radar signal takes 276 seconds to a round trip, to make a round trip between Earth and Venus. So here is Earth. Here is Venus. So if we send it a signal, a radar signal, it goes and come back. So it goes once and come back. It takes overall 276 seconds to travel between the Earth and and Venus. Okay, we know this distance according to the numbers This whole distance for the Earth is 1 AU. This distance from Venus to the Sun is 0.723 AU. So we can find this is A, by the way. We can find this distance between the Earth and Venus by taking 1 minus this number, because this whole distance between the Earth and the Sun, this is where the Sun is 1 AU. So I can take 1 minus 0, this number. So I'm going to have a 7 in here. I'm going to have 12 minus, or 11 minus, sorry. I wanted to go fast, and I really don't want to. Okay, 2.77, 0.277. Okay, so this is the distance we're talking about. So light will go one way and come back and takes 270 seconds. Every second light travels, the speed of light is 300,000 kilometers, or 300 million meters per second, okay? Or 300,000 kilometers per second. But it did not do 1 second, it did 276 seconds to go twice the distance, to go from here to here and come back. So in here, you're supposed to find how much an AU is. Okay, you can find how many kilometers this distance is, D, and divide it by 0.277. It's easy. Half the time takes from the Earth to Venus is half this time, which is 138 seconds to go this distance. Multiply that by 300,000 kilometers, you're going to find how many kilometers there is between the Earth and the Venus when they are at their closest point, when you shoot the laser beam, okay? So you're going to find that distance, divide that number by 0.277, and you're going to find how much a 1 AU is. It should be around, not correct, around 150 million kilometers. That's the correct answer, okay? Around, not exactly, okay? So you might find it slightly more or slightly less. That's your objective in here. So again, 14, Venus and Earth make their closest approach to each other, inferior conjunction, and you can see the picture, and it's similar to the project. Every 583.9 days, use a diagram or math to show that nearly the same side of Venus faces the Earth. Okay. For that, here is the Sun, here is Venus, and here is Earth. Earth goes around the Sun in 365 days. Okay. Venus goes around the Sun, maybe it's closer orbit. I mean, forget about the other side, they are not in proportions. Goes around the Sun in 583. No, I'm sorry. It goes less than that. Okay, we have to find the orbit of we have to find the P for this one. Doesn't make sense. But what they're saying in here is that in its closest approach, they will be in this position after each 583.9 days. So at some point they are here, and the other one is in this position. So some other times they are in opposite direction, but they are going to be in their inferior conjunction. That means they are very close from one another every 583 days. So you're going to take the ratio of these numbers in here, and you're going to find when they will be back in here. And you will find that when the next time they will face each other, they are going to have in simple ratios. And the simple ratios will always point the planet to this position, to a similar position. Again, I can come back into a little bit more detail because we're running out of time in here. But this is basically the idea behind it. Every 583.9 days, they will be close from one another. Any other time, they are far away. Remember, Venus is moving faster than the Earth, so it makes less than 365 days, a lot less than that, to go around the sun. But the Earth is slower. But at some point, 583 or 584 days, okay, to be more approximate, they will face one another, okay? If you do the simple ratios, you're going to find them in simple ratios, and they are in resonance in a sense when this one, so they are, that's why it's facing the Earth in this position always when it comes back, okay? So, and it's in this position, for example, or this position, it's facing in a different side to the Earth. Obviously, Venus is has a lot of clouds and it always looks the same no matter what. Forget about the, because it does, it's not like the moon where you can see the surface. For Venus, you cannot see the surface at all. Okay. Okay. The last question in here, it says Earth covers about 1 degree per day in its orbit around the sun, and the solar day is slightly longer than the sidereal day. And if the Earth spun in retrograde direction like Venus, but it still had the same sidereal period, 23.56 minutes, how long would the solar day be? So let me explain about this thing about the sidereal and all of that, and I'm sure you have read about it because it's part of the assignment where we read things like that. So the Earth goes around its axis in 24 hours. Actually, it's not that correct, okay? Because as the Earth goes around its axis, it's moving around the sun. So this is the sun. So if I look at noon right now to the sun today, okay, and wait 24 hours, the sun will be exactly in the same position as it was yesterday at noon, okay? Tomorrow is going to be the same position as it is today. But what's going on in here, the Earth is actually moving slightly faster. Because if I take a star, for example, which is very far away, where the Earth hardly make any motion around it, then the Earth, and let's look at the Earth, for example, so that star in here, the Earth would have completed a full cycle, and now the star is in the same position as it was before. So it needs to move that extra 4 minutes to face the sun in the same position, to have the sun in the same position. This is the so-called sidereal day relative to the background stars, and this is the regular solar day, okay, 24 hours. So the sidereal day is slightly less than the lunar day, than the solar day, okay? So that is the issue in here. Obviously, the Earth goes around the sun in 365 days, and the circle is 360 degrees. That's why this path in here is slightly more than a degree. So that's basically how you find the distances, and that's how you find the 4 minutes actually because of this shift in there. But what they're saying in here, imagine with me that the Earth is spinning backward. Okay, so in other words, in here, the solar day is 4 minutes longer than the sidereal day. So if the Earth were spinning in the opposite direction, okay, so in this case, we're going to see the sun, and then later on we catch up with the sidereal day. So in this case, as a matter of fact, the sidereal day will be longer than the solar day. So that's the answer to the question, really. So right now, the solar day takes more time, about 4 minutes more than the sidereal day. But if we were to spin backward, actually the sidereal day will be more than the solar day. So this is really the distinction between the two. Again, I can come back in more details about these things. I know this video was a little bit, this recording is a little bit longer than normal, but don't forget you have 2 assignments this week to write about. First of all, do not forget to do your assignment for the lunar observation, number 1. Number 2 is that you have to do the activity at home with a paperclip, just to simulate the tidal forces on Io, on all of the other moons. As a matter of fact, our moon also experiences it too, okay? And so is Earth, but to a lot less extent because of the distance it's involved. And but it's very exaggerated for the case of the moons of Jupiter. So this is basically in a nutshell this unit this week, and you will guys be receiving probably reminders from me on Wednesday to do your observations. So watch for those communications and don't forget to do your own observations. It's critical for your project, and the project is graded. Okay? And it impacts your grade. Okay, I'm gonna stop sharing the screen. And I'm going to stop recording, and I will see you guys next time, okay? And we may have an extra session on this homework to go a little bit more. Did you capture them, Ashley? Okay, the first one has to do with the observations. You have to report that you have to do your observations for the lunar observations this Wednesday. And the second one has to do with the paperclip. Yes, that's the first one. And the second one is the paperclip activity to simulate the tidal forces on the moons of Jupiter. Sounds good? And you're going to actually do that, and you're going to report on it. So it's not just you do it and you say, I'm going to do it, okay? So you're going to report on that. It would be nice if you include a picture of your actual activity. Okay, see you guys next time. Thank you. I'm going to stop the recording. Sounds good?
Yes.
Yes.
Okay, very good. Thank you.